this topic, we cover solution of the 8-queen problem using genetic algorithms. We have discussed the basics of genetic algorithms and trying to resolve now, and we are now moving into actually hardcore gaming, in the sense that if you remember, we've discussed lots about the chess problem, okay, chess. And in that context, we're talking about the 8 queens problem. If you're new to chess, you haven't heard, I suggest go take a look. You don't have to learn what it is, but just that you should be basically familiar with what we mean. Now, there are 8 pieces for one player, and one of which is the queen. The queen is the most precious piece of those 8 pieces, and it has the power to actually attack in all directions, meaning the queen can attack forwards, straight, and backwards, straight, and to the right and left, and this direction as well, this direction as well. So it is very, very powerful, and this is why it probably has been chosen or was chosen to actually work out these interesting problems. Now, keeping this in mind, the queen can attack in virtually in any direction at any length. What we have now, the situation is, the problem is that we have a chessboard in front of us. We have a chessboard which has 8 by 8, 64 squares. And you have a queen, and not just one queen, you have 8 queens. Okay? 8 queens, and you need to place them in such a manner on that board that none of the queens attack each other. Right? None of the 8 queens that are given to us must be placed on the chessboard so that they're not attacking each other. And I can tell you it's a little tricky, because as I just said, the queen can attack in virtually in any direction. So there can't be many placements of those 8 queens that will render each one of them independent of each other without being attacked. If you look at the figure that we have, that's the chessboard, 64 squares, and in each of this we can place one, each cell we can place a queen, and as shown here again, the queen, let's say, is shown in the middle somewhere on the chessboard. So you have a queen there, and then all of these show the attack range of this particular queen, and we have to find somehow other placements so that none of them attack each other. First of all, we need a good representation of this each candidate solution on the board configuration, and we call it as individuals, as we're talking, each board position, let's call it individuals, as in genetic algorithms. And we use the representation shown in the diagram once again. What we have are 8 queens placed at different locations, as you can see. And here's a representation. If you look at, there are some numbers there, 1, 2, 3, 4, 5, whatever, 2, 6, 8, 3, 4, 5, 3, 1, for instance. Now, these numbers represent row-wise location of each queen. The column position corresponds to the place of this number in these 8 positions. So this number 2 actually is placed in the first column, row number 2. That's the position of the first queen. First column, because 2 is in the first position, and 2 means row number 2. So as you can see, you have a 2 there in first column. Then in the second column, you have got a 6, meaning in the second column, go to row number 6 and you will find a queen there. Then the third one, which is 8. So in third column, you will find a queen, okay, in the 8th row. And as you can see, it's there. Likewise. So the last one, for instance, means that in the 8th column, you have a queen in the first row. That's what the representation means. Now, the 8 digits I just explained, and what each of this means. We need, in this case, we defined earlier on as well, we need a fitness function, the evaluation function, a static function, which can tell us which board position is nearer to our goal. Meaning, and how do we know the goal? We know the goal by defining a state on the board, a situation on the board where none of the queens are attacking each other. That's where we want to be. None of the queens should attack each other. And from those given board positions, randomly selected, we are going to select the one that, as I said, they don't attack each other. And we need a method to rate these board positions or individuals. So one fitness function can be to count the number of pairs of queens that are not attacking each other. Instead of counting the one that do attack, let's count the number of queens that don't attack. You can do it both ways. There's no issue with that. So let's look at an example to compute the fitness of a board configuration in the given diagram that we have. So here we have depicted, okay, given this situation, you have got the 8 queens together, and we have shown them purposely the some in white, some in black. Let's look at the fitness function. The first queen, Q1, okay, if you look around it and try to determine all the direction in which it can attack, you will notice that it doesn't attack anyone. Q1 can attack none. It cannot attack none. None of the queens is in its firing range, let's call it. Let's look at the next queen, Q2. Q2 again is in a position where no other queen is in the firing range. Yeah, it might appear to you that Q5 or Q4 in the firing range of Q, they are not. Let's look at Q3. Q3, queen number 3, can it attack someone? And if you look at it diagonally, it can attack. It can attack Q6. Look at Q4. It can attack Q5. Q5 can attack Q4. Q6 can attack Q5. And the reason why I'm saying this now quickly is that because we're talking about the firing range, let's say, of each queen. Likewise, Q7 can attack Q4. Look at it closely. Likewise, Q8 can attack Q5. So putting all of these 8 together, we will count the number of queens that don't attack anyone. And there are only 2 of these. So the answer is the fitness function for this board position returns a result of 2. It has a fitness of 2. And where do we want to be? We want to maximize this fitness function. The result will be a board position which has a fitness function of 8. No queen attacking each other. That's where we want to be. So once representation and fitness function is defined, the solution to the problem is pretty simple. Choose an initial set of solutions or board positions. Remember, we chose 100 words in the discussion earlier on in another topic. So choose initial population and evaluate the fitness of each individual. In the case of that 32-bit problem, we were counting the number of ones, okay, in the binary representation. Here we are evaluating the function of each individual board position that we have selected randomly. And then from those individuals, choose the best. So you could have one board, as you just discussed, have a fitness value of fitness function returns a value of 2. Some could have 3, some could have 0. Some could have 7, for instance, or 6, and so forth. So you will select the best individuals from that population. For crossover, can we take the first half and mix it with the right half? So quickly go through this. So suppose individuals or board positions chosen for crossover. So on the left, you have one board position. On the right, you have another board position with queens placed as they are, as you can see. The board on the left says 85727 meaning column-wise, what is the row location of each queen. So just to reiterate, if you look at the one on the left, it says 857. The 8 means in the first column of this board position, you have a queen in row 8. 5 means in the second column of this board, you have a queen in the 5th row, and so forth. What happens next? We select, let's say, the fitness function. We try to find out the fitness function of each of these. And as you can see, the numbers 2 and 3 in the boxes to the left and the right show the fitness function of each board configuration. 2 is the fitness function for the left and 3 for the right. And then if you look at this diagram, you select 2 parents' board positions as given there and divide them into 2 parts, the left and the right part, and then you generate the children of these. So you take the first child as the head of the first parent, combine it with the tail of the second. As you can see, 8572 taken from the first one and 7165 shown in that number, in that color separately. So from these parents, you generate these children, head and tail put together. Now, what happens next? The individuals on the initial population are shown on the right. We are swapping the tails and the heads. Now we have a total of 4 candidate solutions. And depending on their fitness, we will select the best 2 once again. So we had 4, 2 parents, 2 children. Well, from 2 parents, we created 2 more. Okay, so we left with the original parents and 2 children. So we have now 4. And depending upon the fitness of these 4, we let's select the best 2 once again. So diagram shows where we select the best 2 on the basis of their fitness. The vertical oval shows the children and the horizontal oval shows the parents. So selected individuals, which are the fittest ones, vertical oval, and according to the fitness function, let's see that. Now, similarly, the mutation step can be done. You have mutation, you also flip the bits. Now we're trying to do both things. We have actually done mutation, crossover, as well as mutation. And as you can see that's shown here in the diagram. And we change flip bits at random. And you can see the flip bits are showed in this by these colored numbers. And you end up with another combination, which is 458-27135. And as you can see, the fitness function for this resultant new, let's say, board position is actually 4. So as you can see, we are moving towards a direction where we have moved from that 2 or 3 to a board position of 4, fitness function of 4. And we keep on doing it for each of those selected board positions. If no individual is found, then the process is repeated, and the overall fitness of the population or any of its individuals gets closer and closer to the required fitness level. Now, the only point I want to highlight here is that initially we said that the mutation was random change in the number of bits. We started with only 1 flipping of 1 bit. Okay. Remember in that 32-word thing? Here we can make 2 or 3 or 4. That's up to us. How many, positions do you want to change or move? By the way, the upper limit on the number of iterations is usually used to end the process in finite time. Okay. In chess, you have to make a move when you're playing, that you have to say, all right, give me an answer in 2 minutes, 3 minutes, 4 minutes, so forth. Now, the board positions, as they appear in the diagram, we seem to have found a solution using this genetic algorithm approach. And this, as you can see on this diagram, has a fitness function of 8, and it is represented in the form of that numbers at 4, 6, 8, 2, 7, 1, 3, 5, right? So what we have found using that solution, I've skipped the middle position, but just to illustrate how we went about it. So let's close up and look at the overall flow chart of this process. You initialize the population, random selection, okay. Evaluate the fitness function of each of the population, each one of them, each board position. Ask the question, solution found? Yes. Finish off. Solution found? The answer no. Then move to the left side and make the individuals in the population, you modify them, change them, and then apply mutation. After you apply mutation, you evaluate the fitness function again. So it's kind of a loop that you go through. You could try a 3-queen problem, or a 4-queen problem, or a 7-queen problem, or a 10-queen problem. Find out. You might be able to tell us, no, there's no way that you can place, let's say, 10 queens in such positions, right? So that's what it is. Thank you very much. I hope you enjoyed it.